Hey folks. This is Doug from Mesh Energy. Um, you're joining us for a webinar on a kind of an introduction to renewables, and this is a kind of a brief overview of some of the technologies which are replacing kind of more traditional fossil fuels. An intro to the technologies for ventilation, heating, hot water. And energy generation and energy storage as well, particularly solar. And that's the first part of the presentation. And then we go on to talk about kind of some top tips for specification and design, and then as well as about some of the government subsidies that are available. So I'm expecting this to take kind of 45, 50 minutes and hope you enjoy it. So kind of first things first, just a very, very kind of quick, brief introduction to the business. Mesh Energy, essentially we classify ourselves as independent energy consultants, really a impartial practice that works on behalf of the clients, the rest of the design team, to look at all the options. We're not biased one way or the other, just trying to find out what's best for the building and its occupants. And really, we're able to give, quite considerable kind of teeth and feedback using software and calculation, all kinds of things, not least as well as our experience, to make sure that your designs just get better and you're not left guessing. So very quickly find out what's worth doing, what's not, and getting that specified, etc., etc. And I'll cover that a bit more at the end of the presentation. And also just trying to simplify the whole thing. It's a pretty complicated world out there at the moment. So we're out here to simplify your choices, both again for the design team and for the end client. And unlike a lot of other consultancies, we can offer support at kind of any project stage or across the whole thing. And obviously the earlier we get involved, the better. So that's a really quick whistle-stop tour of the business, and now on to the rest of the presentation. So what we like to do for this particular subject is start with a kind of a case study. It makes it a bit more real, and this is a real project. We did this project with AR Design in Winchester, and this project in the middle of Hampshire. It was on a 25-acre site, very rural, very lucky client. The project budget was about 2 million quid, I suppose, so kind of high-end residential, and quite a sizable property, 650 square meters. The building itself is kind of concrete, poured in situ concrete, external wall insulation, and then kind of sweet chestnut cladding on the outside. And as you can see, quite a lot of glass. So this is the eastern elevation that we're looking at. The house actually has a courtyard in the middle, and this little kind of tunnel thing that you can see underneath the house, that actually opens up to an external swimming pool. So the house actually kind of bridges an external swimming pool. But the long and the short of this story is we got involved at a very early stage. There was a lot of wood on site, so the client was seriously considering kind of biomass and stuff, and the architects had the foresight to get us involved to figure out exactly what was the right thing to do. This site was on oil, so no main gas, and so it had limited options as far as kind of fossil fuel technology is concerned. And most people would have just put in a brand new oil boiler, or maybe an LPG boiler, tank and boiler in the garden. But the client had some foresight here, wanted to do something that was kind of low energy, decided to upgrade the electricity supply to the site and put in the ground source heat pump for the house with underfloor heating, and then did an air source heat pump for the swimming pool to make the best use of those different times of the year for different heat profiles of those two elements of the site. And then to offset that electricity usage, that increased electricity usage, as well as wider electricity usage for the site, putting quite a sizable solar photovoltaic array. We've got some photos on the next slide, which will show you kind of what some of this stuff looks like. But in essence, because we got involved early, we were able to get in over £80,000 worth of government subsidies, which are tax-free. There was quite a sizable reduction, probably about almost 50% on the site running costs compared to oil, as if you just put in an oil system. And we reckon, on balance, he's looking at a payback of about 8 years on this site. So he spent a fair chunk of money at the start, but is is getting considerable government subsidy back, as well as savings that he would have otherwise not been making if he'd used fossil fuel. So again, we got involved early here and decided that biomass wasn't the right thing to do for a number of reasons, and he went the ground source and air source route. And here's just some pictures of what some of this kit looks like. So I know we talk about renewables a lot, but here's actually some installation photos. So on the left-hand side here and middle top, we've got the kind of the main plant room. It is a bit of a squeeze. You can never have enough room in the plant room. But you can see here, we've got the ground source heat pump on the left-hand side photo here in the kind of the bottom right-hand corner. It's like a white box, and this is actually a Valent unit. And the cylinder, you can see there is actually the buffer cylinder. It's not the hot water cylinder, it's a storage cylinder for underfloor heating water. So quite sizable, and just outside the picture is another hot water cylinder for domestic hot water, which is the same size again. So some big chunks of kit, a lot of pipe work, a lot of pumps, valves, etc., etc., etc. Because of the different way that ground source heat pumps work. Not necessarily any more complicated than oil and gas systems. Certainly don't need a load more maintenance, but do require just more pipe work. And the plumbers actually made a pretty neat job of this. Bottom middle is the solar PV array. So the client actually put in 16 kilowatts of solar panels, which is the best part of 50 solar panels. He was lucky enough to have a little orchard here, which he could hide this thing away. And this is what we call a ground array. So it wasn't on a roof, he wanted it tucked away. The architects and the client didn't want solar anywhere near the building to be seen. So we had black panels, put a bit of box hedging in and hid it behind this whopping great big greenhouse that they've got. And then on the far right-hand side, we've got this little box here with these louvers is the air source heat pump. So this unit on its own, no other backup here, is doing all the swimming pool heating. So the swimming pool is kept to around kind of 28, 29 degrees. Lovely, decent cover on the pool. And this little unit heats the pool up at the start of the season and keeps it ticking over through the year. So despite what the other M&E consultants said, who were in charge of the swimming pool, who were keen to specify a system twice as big, we ran the numbers and this unit has been performing absolutely fine. Slightly longer warm-up period for the pool, but it means that you can contain the cost and the size of the equipment, and equipment is actually being used rather than being specified for a once-in-a-year event. So as I say, just an overview here of some of the technologies used for this particular project, and hopefully makes it a bit more real. So the reason we run this case study at the start is because it nicely introduces some of the technologies which are kind of fundamental to the renewable energy mix. And we've got 4 or 5 here which the government support as far as subsidies. And the first of those, which increasingly people have heard about, is ground source heat pumps. If ever you've seen an episode of Grand Designs, you more often than not have seen a ground source heat pump going in. And traditionally, they have been used for larger homes, kind of high-end houses. But that's not the case. There's some small little compact units. They're being used for residential, accommodation, all kinds of things now. So they're not just for the rich and famous. And heat pumps generally, but specifically ground source heat pumps, run on electricity. And essentially these are kind of big, highly engineered domestic electrical appliances. There's no flue, there's nothing combusting. And the reason that ground source heat pumps are kind of famous, should I say, is because they've got some of the best efficiency. So they use electricity as efficiently as possible. And when you look at running costs, if you put all of these technologies together as well as fossil fuel, ground source heat pumps, if they're well designed and well installed, can run and actually offer you the cheapest running costs across the suite of all the heating technology. So although they're using electricity, which is not the cheapest fuel, the way they use that electricity is very, very efficient and it ends up in very low running costs. At the moment, when we put this presentation together, it's probably about 25% cheaper than oil, given how the oil price has plummeted. That's probably not the case anymore, but generally speaking, probably 8-9 years ago, it was about half the cost of oil to run a ground source heat pump. As I say, we're at a bit of a blip at the moment, but generally speaking, it is cheaper than oil by about 25-30% up until recent events. Ground source heat pumps, aren't the cheapest thing to put in. There's a lot of capital equipment, and even the smallest units cost a fair chunk of money to buy the unit, to install it, to do the groundworks. The picture we've shown here is a bulk excavation with the ground loops laid in the ground. But you can do trenches. And I would say there's a few ways of collecting energy from the ground. So as the name suggests for ground source heat pumps, this is about collecting natural energy from the earth below ground, so subterranean. So you can do a bulk excavation like this and put these horizontal loops in, or you can put in vertical boreholes if space is tight. There is also things called kind of water source heat pumps, and this is where it gets kind of a bit fuzzy. So obviously you can have waterlogged ground, and that's still called a ground source heat pump. But if you put these horizontal loops or coils into, say, a body of water, a mill race, a lake, that's sometimes called a water source heat pump. So sometimes they can get a bit blurred, but essentially they're doing the same thing. And it's worth noting that ground conditions for this technology do affect its performance. So there's a saying that goes, the wetter the better. So some people think that waterlogged ground historically is pretty poor, but actually it's very good. The diagram that you can see here, the picture, which has kind of sandy and chalky soil, is actually on the side of not so good. If this was waterlogged clay, absolutely spot on. You could have a smaller array by probably about half of that. And so that's why understanding ground conditions for this technology is absolutely key. Air source heat pumps, which are a lot more popular. There's probably about 4 or 5 times as many air source heat pumps in the UK that have been installed as ground source. They are cheaper to put in. They're still, in many ways, very similar to ground source technology, but rather than collecting energy from the ground, they're taking ambient energy from the air. And because underneath the ground, the temperature is much more stable, let's say 10 or 12 degrees through the year, ground source heat pumps are kind of reliably efficient. Whereas for air source heating, because you've got the varying air temperature, their coefficients of performance or their efficiency, the way that they use electricity, does vary from season to season. So in the summer, when you've got lovely and warm weather, you can get bags of energy out of an air source heat pump. And actually, because of the very warm air source heat pumps become more efficient than ground source heat pumps. And that's why for many years they've been used for swimming pool heating, for example. And particularly if you've got a kind of a summertime only heating requirement, they can be really, really good. However, in winter, when you might be heating a house or providing hot water, they are less efficient. The air temperature may fall to 0 or below. Air source heat pumps can easily work at that temperature, and that's a common myth that they can't, but they are less efficient. So generally speaking, for just house heating and hot water, air source heat pumps are less efficient than ground source, but actually for a swimming pool application, they would be the obvious choice over ground source heating, if that makes sense. So it really depends on the seasonality of how you're using these things. And as houses become more efficient, the differences between air source and ground source systems does shrink. They've obviously got different performance levels, but if the actual size of the units are small anyway, because you've put a lot of effort into the fabric efficiency and the air tightness of the house, the differences become much smaller. But also the cost reduce as well. And air source heat pumps will always be cheaper than ground source heating because there's far less civil work required, and the units are designed to last not quite as long, and they're just they're just simpler units to manufacture. So typically, as these pictures show, you'd have on the far right hand side image here, you've got these kind of single or double fan units. This is a pretty typical domestic unit for kind of a 3 or 4 bedroom house. And then on the left hand side there, some of them have split systems, have like an indoor box that looks a bit like a wall-hung gas boiler, and then you've got a separate hot water cylinder here. You don't get kind of combi air source systems, so you need a hot water cylinder to store water. And compared to mains gas, so I've got a little comment here about 10% cheaper than mains gas. This is the running costs for kind of new build, not necessarily the installation costs. So the installation costs are more than the gas boiler installed and commissioned. But if you looked at it on a new build like for like basis, if you had 2 identical houses, an air source heat pump would be roughly about 10% cheaper to run than gas. For retrofit applications, you've got to be a bit careful because the gap really closes down. And in some retrofit applications, air source can, depending on the emitters and the amount of insulation and stuff that you've got, can be more expensive to run than gas. So you've really got to crunch the numbers when you look at the technology to make sure it's going to be right, and it's going to give you the savings that you're after. The only last thing to bear in mind about air source heat pumps is you may need planning permission. In fact, actually, that does remind me, for ground source systems now, you actually need permission from the planners to say that the ground loops are permitted development. That's a relatively recent change. So you do need planning for ground. Air source, sometimes it is required, sometimes it isn't. The planners are obviously concerned about noise and looks. And certainly if you've got more than one of these, they'll be very, very interested. So just bear that in mind, speak to your planning officer before you kind of charge ahead. Solar photovoltaics, most of us will be familiar with solar PV. It's kind of everywhere in farmers' fields in the West Country and throughout the south of the UK, and it's been used a heck of a lot in the UK. I think over the last decade, there's been over 600,000 installations, which is a fantastic quantity. And these, to differentiate the two between solar thermal and solar photovoltaics here, solar photovoltaics is for generating electricity, whereas solar thermal is for generating kind of hot water. And the reason that solar PV has been so popular is because it's very, very reliable. We know where the sun is all the time, and it'll work on bright days. Is cheap and has become significantly cheaper than it was a decade ago. Prices have plummeted for solar PV, and it's simple. It can be put on so fast. There's no plumbing. There's very little maintenance required with solar PV. And there's been some really exciting developments with kind of product integration into roofs and other kind of building materials and facades and things. So it comes in multiple physical forms. And certainly with battery technology, the advances in solar over the next decade coming, even 5 years, I think will be quite surprising. There's a big charge to make solar PV technology kind of more invisible, and the work that Tesla's been doing on solar tiles. There is actually a company in the moment called GB Sol in the UK that are selling solar tiles, but it's likely the Tesla offering will probably be about half the price of those. So it's been a long time coming. It will come. Now that Tesla have sorted the Model 3 out, I think the solar tiles will rapidly follow to the UK. They started doing some early installations in California, and hopefully getting some of the bugs out. But the price is really considerably dropped for solar PV, and it's got a long way to go. A lot of money being spent on development of solar. And I think generally speaking, people are kind of love the idea of being able to be their own kind of power plants, and so as long as we can do that kind of in an aesthetically sensitive way, and it makes sense from a cost point of view, I think a lot of people would love to make solar PV a kind of a key part of their buildings. And when you look at some of the REBA targets at the moment, 2030 to be specific, I think by the end of the decade, really a house being built without solar is going to really struggle to meet some of the tight targets that are set. So it's becoming a real kind of utility for buildings rather than a kind of a nice to have as well. So along with kind of solar, the advances in kind of solar PV is battery technology. And I say advances in battery, we are just at the start of a very, very steep curve with battery tech. The advances in EV kind of electric vehicle car technology have led to really rapid advances in home battery storage. And batteries here are used for a number of reasons in the home. They're used for storing electricity, and that can be free electricity from solar, but it can also just be electricity. These batteries can be put in without having solar on the property. You can essentially, if you use the kind of the economy 7 analogy, you could store electricity when it's cheap at night and then use that electricity when otherwise we would be paying kind of high tariff rates. So they're quite a flexible technology. You can increasingly use systems to protect you against power cuts. So a bit like good old fashioned kind of uninterruptible power supply you used to have for laptops and PCs. There are many product options. I've shown a picture here of a Tesla unit. And I always get asked this, how big is this Tesla unit? Performance-wise, this would probably keep a 3-bedroom house going for a day. It's 14 kilowatt hours. And dimensions-wise, it's probably 1.5 meters tall by probably 800-900 meters wide. It's probably about 4 inches or 100 millimeters deep. So it's kind of like a chunky picture frame that you can hang on your wall or put on the ground. And if you buy multiple ones, you can stack them one in front of the other. Typical costs, I mean, a Tesla battery at the moment, for that capacity, probably paying about £8,000 installed. But there are many other options. You can get tiny batteries. You don't have to go for one sexy looking product. There's all kinds of options. So yeah, lots and lots of choice. And it really does depend on the application. It's not kind of one product fits all. You've really got to have a think about, you know, what you're after from the battery and then design the system appropriately. There are no subsidies at the moment. People ask about whether battery tech needs to be subsidized. I don't think it does. I don't think it does. It's kind of, numbers wise, it's kind of a kind of a break-even point about whether you actually get any money back after the kind of 10-year lifetime of the batteries. But there are no subsidies planned. I don't think there needs to be, certainly in the current economic condition. I think the government's going to be a bit sticky about handing out further subsidies, but I don't think battery tech needs it. I think as solar technology becomes more ubiquitous and car technology moves on, home battery technology will benefit from those price economies of scale and decrease. So I don't think there's any requirement for further assistance on batteries. So look out for battery technology, definitely. I'll quickly run over just biomass. It's one that the government's still paying subsidy for, and so it's worth mentioning. But you're back to burning solid fuel here: pellets, chips, logs. Pellets and chips can be automated. You need a lot of space. Pretty well engineered bits of kit, really, but still you can't get away from the fact that you need deliveries to site. You've got to store, you know, bulk quantities of chip. Great for kind of older buildings or large kind of estates. These are used a lot in Germany for kind of district heating schemes where you can have one centralized big building. The problem is with very, very highly insulated buildings nowadays, this technology, my personal opinion is it's kind of like, it's like having a heavyweight boxer in the ring when all you need is a kind of a bantamweight, really. So great for niche buildings used by National Trust a lot, used for leaky old farmhouses and things. But for modern buildings, I think biomass has limited scope going forward. But as I mentioned in here, just for completeness. And then finally on the technologies, just about mechanical ventilation and heat recovery. Again, being used more and more, ventilation and certainly the heat recovery bit of this is becoming increasingly important to drive down energy usage in buildings. So we make buildings more airtight, and we use these systems to better ventilate the building. We don't need trickle vents anymore. And then in summer, as I've talked about in some of the other talks, we use kind of natural ventilation as well as mechanical ventilation, heat recovery, to make sure the building functions properly in the summer, as well as being very efficient in the winter. And the heat recovery elements of mechanical ventilation, heat recovery are quite considerable. I mean, ventilation losses in the building are increasingly a larger chunk of your energy bill. So being able to recover, you know, 95% of the energy from that waste heat that would otherwise be leaving the building is becoming really important. These are electrical devices. In most cases, they might cost you 60 to 80 quid for a single unit to run of a year. So they are running a small little fan, but it is a tiny amount of energy that they're using, even though they might be running all the time. And if it's designed properly, a lot of people are concerned about noise here. If it's designed properly, noise is not an issue. It's all about using rigid or semi-rigid ducting, proper design, getting involved early in the design. This does potentially affect the structure of the building. So the earlier that you consider any of these technologies, but not least MVHR, the more success you're going to have with your project. So I've just got a few slides here quickly on spec and design. They're just a couple of key tips against the technologies to help you out. Ground source heat pumps, particularly, the big thing here is a kind of a rule of thumb about land area that you need for the loops. And if you assume kind of twice the kind of the livable heated space of the building for horizontal collectors, whether it's in trenches or a bulk excavation, that's going to give you a fair idea of the size that you need. The other big thing here is about plant room space. So a minimum, a bare minimum for a small domestic installation of about 3 square meters. For larger projects, it could be in excess of kind of 10, 12 square meters that you need. Lots of kit, lots of pipe work. Don't scrimp on plant room space, because you'll be having an awkward conversation with your client if you do. And then the final thing about this technology is about planting. So location of the ground loops here. So don't try and put them in open spaces that aren't going to be developed in the future. They can go under planting, but planting an avenue of oak trees over the top of it, or poplar trees or something, you're onto going to have issues later on in the development, because nature always wins. There's no issues with putting this under kind of farmland or grass. It won't affect the growth of those things. These pipes are buried about 1.5 meters deep, roughly speaking, so not going to affect light planting. But as I say, putting this stuff under car parks as well, again, impervious car parks are going to create an issue, because these systems work well with water and moisture. If you put a car park over the top, essentially an umbrella, or a big tree, it's an umbrella, and you stop water getting to the pipework, moisture getting to the pipework, and that can create real issues. So don't do it, and bear that in mind. That's kind of the top tip. Air source heat pumps, lots of different varieties here, much better suited for kind of smaller buildings. So lots of different options, can be used in all kinds of different ways. So very, very flexible. The other thing I was going to say finally here, which I always pick up on, is obviously try and locate away from social areas. These things aren't, they are quiet, but they're not whisper quiet. Go and see one if you're at all unsure before specifying one, but also worry about drainage. The outdoor units, because of the low temperatures that they get to in winter, most of them enter into a kind of a defrost cycle to help clear the fins at the back of the unit from any slight light frosting, and that means dripping water in the winter. So if you don't have a drain pan and don't have somewhere for that water to go, it can cause issues with icing. For the bigger units, that could be a couple of litres an hour. So hard surfaces, having that run out, you're going to end up with an ice rink and a pretty unhappy client. And certainly if they're elevated, you're going to end up with issues also of water raining down in the middle of winter. So do pay attention, particularly to drainage. Solar PV and solar thermal, they're kind of the same thing really, as far as the kind of the tips here. Ideally, kind of south facing at 30 to 40 degrees is ideal for the UK. But actually, they're very, very flexible. There's a lot of interest in hiding solar panels at the moment, and that's fine. On a flat roof, to give you an idea, if a solar panel's flat on its back, you get about 90% of the output as you would do if it was south facing at 30 or 40 degrees. So you don't lose much. And likewise, if you turn the panels 90 degrees to due east or due west facing, you only maybe use kind of 10 to 12% of efficiency also. And that's why this technology has been so popular on houses, because the outputs are very, very good, even if it's not dead due south facing. The other big thing to bear in mind is shading. What you're trying to avoid is heavy shading. The odd wafer thin aerial is fine, but swamping chimney stacks or having big aerials and stuff near these things, which then cause issues during the summer with solid shading, can be a problem. There has been technology advances that allow individual panels to shut down and not affect the rest of the array if one is covered, but as a general design principle, you're trying to keep these things in open sunlight and open view of the sky. And of course, bear in mind deciduous trees during the summer months as well. The final thing I want to pick up on here is it's kind of boring for a lot of people, but my goodness, is it critical? So do pay attention to this bit. Electrical supplies, electricity supplies to buildings. As buildings become more electrified and we consider things like electric vehicle charging points, as well as getting off oil and gas and possibly looking at heat pump technology, our electrical supplies and electrical systems in the house become more important. And generally speaking, we find there comes a point when seriously, you need to start thinking about three-phase. Germany, as a standard, puts three-phase into buildings. We still stick around putting single-phase into domestic dwellings. But more and more of our clients are upgrading to three-phase. And to give you a reason why, we're all used to having quite big fuses for our electric cookers, for our fan ovens and our hobs. And generally speaking, historically, those have been about a third of a standard supply. So you might have a 100 amp supply to a building, and those cookers have a kind of 32 amp breaker on them. Electric vehicle car charging has a similar sized one. So if you're cooking on electricity, you've got electric vehicle car charging point, say 7 kilowatts, that's another third of your board taken up. And a heat pump could do the same again. So then you've got heating, you've got kind of small power, lighting, other things that use electricity in the home, and you start to get over that 100 amps. So that's why it makes sense to look at a three-phase supply, and particularly in bigger properties, particularly those with pools and just heavier electrical use. Three-phase is almost a kind of a must, really. So do bear that in mind. The other reason is financial risk to the project. We've recently seen quotes of high hundreds of thousands of pounds for upgrading to three-phase. It's a real unknown, and you just can't tell how much it's going to be. So finding out early so you can put that in the budget is really, really key, rather than finding out at the last minute and not having any money for it. Sometimes it may only cost £1,000 to upgrade to three-phase. In some people's cases, it can be six figures. So the fact that there's such a massive range there means that you need to get your head around it as an earlier stage as possible. And it's free. It's a free application to the DNO. We can support you with that application, but essentially you get an answer within a few weeks with a quote, and you can be pretty sure that that's what it's going to cost you to upgrade after they've had a look at the network. And then finally, just the final bit of this webinar on the domestic renewable heat incentive. So I talked to you about government subsidies, and almost all of those technologies, bar batteries and MVHR that I discussed a few minutes ago, are supported by government subsidy. So this is a scheme that's been around for years. I mean, it's probably been around for probably about 5 years now. There is a commercial version and there's a domestic version. I'll just talk to you about the domestic version and then briefly mention the commercial one. But domestically, very, very poorly marketed. A lot of us have heard about the tariffs which you get for solar technology. Those have come to an end. This is subsidy payments for heat and hot water generating technology. So these are paid for 7 years. They're tax-free. And the figures I've got there for air source, ground source, biomass and solar thermal are the kind of the maximum payments that you can get. So over that 7-year term, what's the total sum, tax-free sum that you can get? So there'll be tax, you won't have to pay tax on these figures that you get. Air source, ground source and biomass are all capped. So if you live in a whopping great big house, you don't necessarily get more than, say, a 4 or 5 bedroom house. And the tariff levels are different, generally speaking, because of the cost of the technology to put in. But when you shake down the numbers for this, it works out about a kind of a 7 or 8 year payback for the technology. So what I'm saying is here, if you take advantage of this subsidy, which can be used for new builds as well as existing buildings that are putting this technology in, once you factor in the cost savings over fossil fuel as well as this tax-free subsidy, you essentially pay for the installation cost, the total installation cost of the technology. And this medium-term outlook and being aware of these subsidies is really, really critical. So this is why we factor this into the feasibility studies that we do. A lot of people see renewable technology as a very kind of expensive, kind of capital-intensive option compared to oil and gas. But here's the other flip side. This is the kind of money that you get back in your pocket for being a bit more progressive. And the commercial scheme is slightly different to this. It's a 20-year scheme. There are a few tricks that you can play with it, certainly on domestic properties if you have more than one building actually on your site, so you can access the 20-year scheme. The subsidies are lower, and certainly if you're spending more money, there are some economies of scale as well, so you can actually get your money back quicker under the commercial scheme, generally speaking. So I think that kind of wraps it up for the webinar. Hopefully you found that informative. We can cover any of this stuff as a company. In fact, I'll show you this final slide really, which just kind of gives you an overview. I said Mesh Energy can help you at any stage, and we really can do so. Any of the REBA plan of work stages here, we can help with, you know, bog standard energy calculations that you might need for government regulation, thermal design, dynamic, you know, building physics modeling, but feasibility studies. So the technologies that you've seen today, we can help with feasibility studies for any of those, figure out what's right, what's wrong, crunch the numbers, shake down the benefits, and then design these systems. You know, we design these systems, do full M&E packages, recommend installers, MCS accredited installers, who are the accredited installers for renewable tech, so you can get the government subsidy, and then help you out with the, you know, reviewing tenders, and then at the end getting the subsidy at the end of the project. We even do post-occupancy evaluation and energy monitoring as well. So for now, guys, thanks for listening. Join us next time. We're doing a long series of Wednesday webinars, and hope to see you at one of those. Take care.